Do you know nearly 10 million people died of cancer in 2020? If we have a tool to show the picture of what's going on in our cells in real time, we may get an insight into the mechanism of cancer so that we can detect the sign of it in advance and save as many lives as possible. One way to achieve the tool is using fluorescent dyes. Dye is injected into the cell and combined well with specific structure. With a beam of light, it will absorb the energy and start to glow, so the structures can be seen clearly under the microscope. Fluorescent dyes can be divided into different types, including one-photon and two-photon absorption one. Basically, one-photon absorption dye molecule only absorbs one photon energy to emit fluorescence, and 2Pa absorb two photons energy. One photon is good, but 2Pa dye are better for seeing the details. However, the light intensity that 2Pa dyes emit is comparatively low. To see more clearly, there should be more photon crossing through a certain area, namely larger cross-section. That's the reason why it is important to develop better 2Pa dyes. And my project is about using computational chemistry to look for potential 2Pa dyes. Computational chemistry focuses on the application of quantum mechanics to chemical systems. Generally, we can take a system from the simple one like hydrogen to the complicated one like enzyme catalyzed reaction in body. By setting different approximation and solving Schrodinger equation, relatively accurate and time-saving results can be calculated using the top-level computers. And that's the point of computational chemistry. We can streamline the searching process significantly by making predictions about what compounds are promising to use as 2Pa dye and inform experimentalists to decide what to synthesize instead of a tedious and wasteful trial and error process. They can also understand the reasons behind the cross-sections that molecules act to better design 2Pa dyes. My research focuses on DIPYS, a small, elegant molecules with different stability and one photon absorption property, and also low toxicity, which makes it widely used in biomedical research. It is very promising for 2Pa dye, but its cross-section is very low. So I want to know whether 2Pa is improved when I change the boron to other similar elements, and how can I modify these molecules to enhance their cross-sections. By comparing the calculation results, I find that the other DPs have the analogous 2Pa properties like BODP. However, if we add more alternating single and double bond structures to these molecules, their enhancement acts very differently. With these results, I find which DPs have more potential and thus need to be paid more attention to, and also I can know what approximation methods we use can get the cross-section correctly and rapidly. That's all my content about the research. Thanks for your listening.